When we talk about application security testing, the most important thing to understand at the outset is that no single viewpoint can reveal every meaningful weakness.
Software behaves differently when you look at its source, when you watch it run, and when you observe how it reacts to real inputs under real conditions.
Each testing approach brings a different lens, and those lenses expose different categories of risk. If you expect one method to tell you everything, you will either miss serious issues or drown in misleading results. The goal of security testing is not perfection, but informed visibility across the lifecycle of the application. Once you understand why multiple viewpoints exist, the rest of the discussion becomes much more intuitive. Static application security testing works by examining source code or compiled bytecode without executing the application. It looks for patterns that are known to be risky, such as unsafe function calls, missing validation, or improper handling of sensitive data. Because it does not require the application to be running, it can be applied very early, even before a build is deployable. This early visibility is one of its strongest advantages because it allows teams to identify potential issues while changes are still cheap. Static analysis can also see code paths that may be hard to reach during normal execution, which is useful for identifying latent risks. However, it is important to remember that static tools reason about possibilities, not about actual runtime behavior. That distinction explains why static testing often produces false positives when used without sufficient context. The tool may flag a risky pattern that is technically present in the code, but never reachable due to surrounding logic. It may also lack awareness of how data is validated or constrained elsewhere in the application. Without understanding the full execution flow, static analysis errs on the side of caution, which is appropriate for a machine, but challenging for humans reviewing the output. This means results must be triaged by people who understand both the code base and the security implications. Static testing is most effective when its findings are treated as hypotheses to be evaluated, not as confirmed vulnerabilities by default. Dynamic application security testing takes a very different approach by interacting with a running application. Instead of reading code, it sends requests, manipulates inputs, and observes responses to see how the system behaves. This mirrors how an external attacker would probe the application, making it valuable for identifying issues that only appear at runtime. Dynamic testing can reveal misconfigurations, authentication weaknesses, and injection flaws that depend on how components interact when deployed. Because it works against a live system, it inherently includes environmental factors such as middleware, libraries, and runtime configuration. This makes its findings feel more concrete because they are based on observed behavior rather than theoretical risk. At the same time, dynamic testing has its own blind spots that you must account for. It can only test what it can reach, meaning any code paths that are not exercised by its requests remain invisible. If a feature is hidden behind specific workflows, roles, or rare conditions, dynamic scanning may never touch it. Logic flaws that require complex sequences of actions are also difficult for automated tools to uncover. In addition, dynamic testing cannot see internal state changes directly, so it may miss subtle issues that do not produce obvious external symptoms. This is why relying solely on runtime scanning can create a false sense of coverage. Interactive application security testing sits between these two approaches by observing applications from the inside while they are running. It instruments the application during testing, allowing it to see how data flows through code paths as requests are processed. This internal visibility provides context that static analysis lacks and precision that dynamic testing cannot achieve alone. Because it understands which code is executing in response to which inputs, it can often reduce false positives while still identifying real issues. Interactive testing benefits from being deployed in test environments where functional tests are already exercising application behavior. In effect, it watches the application think while it works. The strength of interactive testing lies in its combination of runtime awareness and code-level insight.
When an issue is detected, it can often point directly to the line of code and the execution path involved.
This makes remediation faster because developers do not have to guess which part of the system triggered the finding.
It also allows the tool to distinguish between data that is validated or encoded and data that is not, based on actual execution rather than assumptions.
However, interactive testing still depends on coverage because it can only observe what actually runs. If certain features are never exercised during testing, they remain unobserved. Coverage is a shared limitation across all security testing methods, even though it manifests differently in each. Static analysis covers everything in the codebase, but without knowing which paths matter most at runtime.
Dynamic and interactive testing cover only what is exercised, but with much richer behavioral insight.
This means the quality of your test cases directly affects the value of your results.
If your functional testing is shallow, your security testing will be shallow as well. Comprehensive testing requires intentional effort to exercise critical workflows, edge cases, and error paths. Without that effort, even the best tools will provide an incomplete picture. Authentication handling becomes a practical concern as soon as you move beyond publicly accessible functionality. Many meaningful risks exist behind login screens, role-based access controls, and multi-step workflows. If a testing tool cannot authenticate properly, it will only see the surface of the application. This can create the illusion that an application is relatively safe when, in reality, the most sensitive features were never tested. Configuring scanners to handle authentication correctly is often non-trivial, especially when sessions expire or tokens rotate.
Getting this right is less about the tool and more about understanding how the application manages identity and state.
Once findings are generated, prioritization becomes the next critical step. Not all issues are equal, even if they share similar technical labels. Exploitability matters because a flaw that is easy to abuse poses a different risk than one that requires rare conditions. Data sensitivity also matters because exposure of trivial information is not the same as exposure of regulated or confidential data.
Context matters as well, including whether the vulnerable component is internet-facing or internal.
Effective prioritization turns raw findings into actionable risk management rather than a backlog of undifferentiated alerts. Integration into delivery pipelines changes security testing from a periodic activity into a continuous one. When testing is automated and triggered during frequent releases, it becomes part of the normal rhythm of development rather than an exceptional event. This allows teams to detect regressions quickly and avoid reintroducing previously fixed issues. Pipeline integration also encourages smaller, more manageable sets of findings because changes are incremental. Over time, this builds a feedback loop where developers learn which patterns trigger findings and adjust their coding habits accordingly.
The result is not just better detection, but better prevention.
Baselining plays an important role in keeping this process sustainable. By establishing a known set of existing issues, teams can focus attention on new findings introduced by recent changes. This reduces noise and prevents the same unresolved issues from dominating reports release after release. Baselining does not mean ignoring old problems forever, but it allows remediation to be planned realistically rather than reactively. It also helps measure progress by showing whether the overall risk posture is improving over time. Without baselines, security testing can feel overwhelming and discouraging. Verification closes the loop by confirming that fixes actually change application behavior in the intended way. Retesting after remediation ensures that the vulnerability is resolved rather than merely masked. It also helps catch partial fixes that address one code path but leave others exposed. Verification reinforces trust in the testing process because teams see a clear connection between findings, fixes, and improved outcomes. Over time, this builds confidence that security testing is producing real value rather than busy work.
It also supports accountability because changes can be tied to measurable results.
When you put all of this together, the central idea becomes clear. Static, dynamic, and interactive testing are not competitors, they are complements.
Each one sees something the others cannot, and each one compensates for the other's blind spots.
Used together across different stages, they provide a layered view of application risk that is far more robust than any single method.
The real skill is not choosing one tool over another, but understanding how to combine perspectives to match your development process.
When applied thoughtfully, these testing approaches help teams catch weaknesses earlier, respond more intelligently, and build systems that fail less often and less severely. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.